Hello, everyone. Happy New Year. Welcome to the next talk in our Golden Webinars in Astrophysics series. I hope you are all healthy, safe, and well. We are very excited to bring you a very interesting pack of the next batch of speakers in this series. So our speaker today is Professor Stacy McGaugh, who is a professor of astronomy at the Case Western University in Cleveland, Ohio. My name is Thomas Puzia, and together with Elizabeth Artur de la Villamois, we have organized today's webinar for you. As in our previous webinars, we have, of course, arranged again for simultaneous language interpretation provided by Patricio Gonzalez, who will be simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación, que parece como un globo, que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom. Y seleccionar español, obviamente. Es la aplicación Zoom, no es el browser. We would like to acknowledge the generous support of the Center for Astrophysics and Related Technologies, also known as CATA, for its Spanish acronym, for making this series possible.
Thank you so much for all your feedback and comments. If you're watching a recording of this talk on YouTube, please leave your comments below. If you would like to support the Golden Webinar series or give us feedback, please send us an email. If you have any questions during the talk, please type them in the Q&A window. You can also upvote questions and comments on them. We will select the best questions for the discussion after the talk. Before we begin, I would like to briefly introduce our other panel members that are with us today. In the panel, we have Stacy, Patricio, Thomas, and myself. From the Institute of Astrophysics at PUC, we have Paul Egenthaler. We also have the great pleasure to welcome our guest panelists today, Rohan Rahatgaonkar, from research intern at Gemini Observatory, Matthew Taylor, postdoctoral research fellow at the Herzberg Astrophysics National Research Council of Canada, Victoria, Indranil Vanik, postdoctoral research fellow at the University of Bonn, Emanuela Pompei, astronomer at the European Southern Observatory at La Silla, Davor Krajinovic, astronomer at the Leibniz Institute for Astrophysics in Potsdam, Germany, Cole Miller, professor of astrophysics at the University of Maryland, Paul Hoyningen, professor of philosophy, Institute of Philosophy at the Leibniz University of Hanover, Germany, and lecturer at the Department of Economics at the University of Zurich. And finally, we have our excellent Q&A manager, Ricardo Acevedo.
So it is our great pleasure to introduce Stacy McGaugh as our speaker today. Stacy was a student at MIT Princeton in 1985 and completed his PhD at the University of Michigan in 1992. He held research fellowships at the Institute of Astronomy at the University of Cambridge, the Department of Terrestrial Magnetism at the Carnegie Institution of Washington, and Rutgers University. From 1998 to 2012, he was a professor at the Astronomy Department at the University of Maryland, College Park. Stacy is currently professor of astronomy and department chair at the Case Western Reserve University in Cleveland, Ohio, and the director of the Warner and Swayze Observatory.
His research interests include low surface brightness galaxies, galaxy formation and evolution, tests of dark matter and alternative hypotheses, and measurements of cosmological parameters. During his career as a researcher, he published more than 120 papers on these topics. As an expert on low surface brightness galaxies, he demonstrated that these dim objects appear to be dark matter dominated, providing unique tests of theories of galaxy formation and modified gravity. And so we will now hand over to Stacy to tell us about dark matter and gravity, what is the universe made of, and which is calling the shots.
Thank you. Thank you for having me. It is a pleasure to be here, if only in a virtual sense. It has been many years since I had the good fortune to visit Chile, so I am sorry I cannot be there in person. However, it is also great that we have this technology that we can communicate in these trying times. So, buenas tardes. I apologize not to speak in Spanish myself, but no tengo muchas palabras. So I will rely on Patricio to do the translation. I would like to start with just a little reminder of scale, that we live on a tiny planet in a giant universe. So the population of Santiago is about 6 million people, más o menos, depends on how you count the metro area. But to astronomical accuracy, that's a good number. And so there's a picture of Santiago on the left from the NASA Landsat satellite. And on the right is an artist's rendition of our Milky Way galaxy with the scale there noted in the bottom left corner. That's 500 quintillion to 1, a number that makes no sense whatsoever to our minds. So I would note that the mass of stars in the Milky Way is about 60 billion. So roughly speaking, that's 10,000 stars for each and every person who lives in Santiago. So if we had some magic Star Trek-like technology and we built a spaceship for each and every individual person in Santiago to explore the galaxy, and you could travel instantaneously from here to there to wherever, it would still take, you know, each person in Santiago, every man, woman, child, small baby, to visit 10,000 stars personally before we had explored the entire galaxy. That would take even traveling instantaneously, which is of course impossible over the vast reaches of space, but that would take 30 years just visiting one star at a time and spend only a few hours there. So I hope that gives a little better perspective on just how vast the galaxy in which we live is. There are really a lot more stars than there are people. Now, I will talk a lot about galaxies as individual objects. So to give you some flavor for what those are like, here are a few pictures from the Hubble Space Telescope, ranging from a very massive spiral galaxy, UGC 2885, through something that's more on the scale of the Milky Way, to an intermediate mass spiral and a very low mass dwarf galaxy. Even the low mass dwarf galaxy here has something like 30 million stars, so that's still a lot more than the population of Santiago. And that is a tiny galaxy by the standards of galaxies. So these yellow bars try to illustrate the scale. So that's 100 kiloparsecs, several 100,000 light years. And at 2 kiloparsecs, that's the same as that bar over there. So we'll try putting that on the same scale. But before I go there, I'll note that galaxies don't only exist over a large range in luminosity, the total number of stars they have, but also in how fast they rotate, what their surface brightness is, whether the stars are concentrated or spread out. And they're also made of gas. So there are galaxies that are almost entirely stars and others that are almost entirely gas, very few stars. And putting all those on the same scale, that is how they would appear together if they were all at the same distance. This is the Milky Way sized galaxy, and you can see it's very small compared to this massive spiral galaxy, UGC 2885, which happens to be one of the most massive spiral galaxies in the local universe. And the little dwarf, DDO 154, you would not even notice unless, I put the label there. So there really is an enormous range that we need to understand here. This is a portion of the Hubble Ultra Deep Field using the Hubble Space Telescope to look at one small patch of sky. And you can see lots and lots and lots of galaxies, some nearby enough to see the spiral structure, some so far away that they appear as little more than dots. But just by eye, you can see that there are hundreds of galaxies in this tiny, tiny portion of this image, which is only a tiny fraction of the entire sky. The entire sky is about 20 million times larger in area. So there are a lot of galaxies out there. Now this is a map of the entire sky. It wraps around in the same way that a map of the Earth would do, except rather than looking down at the surface of the globe projected in this way, we're now looking up at the sky. So that wraps around, and every dot in this image is one galaxy. And so to remind you what that means, I've put a picture of a real galaxy in there, and that entire thing just shows up as one dot there. So there are roughly 100 billion galaxies within the observable universe, each with order of 100 billion stars. So that's big. There's nothing in the human imagination that can compete with that, with the possible exception of our own egos. Now, we know a lot at this juncture in science, especially about gravity, which is the force that dominates the universe. It tells us how things move, planets orbiting the sun, stars orbiting each other, and presumably galaxies in the entire universe as a whole. So that theory, that entire rich background from centuries of progress and understanding is summarized in Einstein's theory of general relativity, which provides a really elegant description of the universe in which we live, provided that it is full of non-baryonic cold dark matter. So what does that mean? There has to be some substance that does not meet the eye. It has to be slow moving and hence cold. And non-baryonic is a technical term to mean it's not normal matter. It's not the stuff that we're made of. It's something quite outside of that. And so to try to keep track of this, I sort of made this diagram a quarter century ago. And at the top of this dark matter tree are all the ideas that people have had for what kind of things the dark matter might be. And down at the bottom are the roots of the problem, i.e. what do we think, what is the evidence that makes us imagine that the universe is filled with this dark matter? So I'll go through that briefly, and I can't possibly address all of these things in one talk, but I do want to give you some flavor for the diversity of things, because there's lots and lots and lots of evidence at this point. One famous piece of evidence that I will speak about a lot is the rotation curves of spiral galaxies. If you measure the rotation speeds, how fast things are going around in these using the Doppler effect, then that orbital velocity is a function of the distance from the center. It goes up and then it more or less flattens out. But you can compute from the gravity of what you see that this ought to go down. And so that is not the case leads us to infer that there is some extra mass there that we cannot see. The same thing is true for clusters of galaxies. Now, each one of these fuzzy blob is in itself a giant galaxy, which are bound together in a giant clusters of galaxies. And these are rare objects that they show lots and lots of evidence for this kind of a discrepancy. One is simply that the relative speeds are too fast. So just as a spiral galaxy is rotating faster than you'd expect for the stuff that you can see, that's also true for the relative motions of the individual galaxies in this cluster. In this particular cluster, you can see these arc-like figures. These are the results of gravitational lensing, as the mass of the cluster itself is bending the light from background sources, stretching them out into these arcs. And again, gravity will do that, but only if there is more mass there than meets the eye. And finally, in clusters, there is X-ray gas. Basically, in between the galaxies, there's a very hot, if diffuse, intra-cluster medium of gas that emits X-rays. You can see that super hot, millions of degrees Kelvin. And that could not be contained by the cluster's gravity unless, again, there is a lot more mass than meets the eye. So that was known long ago, in the 30s already by Zwicky. Oort had already at that same time pointed out that within our own Milky Way, there seems to be a discrepancy. We've often hoped that the density, the mass density parameter of the universe would have this magic value, which I won't go into in great detail because we don't believe that anymore, but that was long hoped to be the case. But there's also the large scale structure of the universe that we saw in this map before. And just looking at this by eye, you can see that there is a lot of structure. There's these long walls of galaxies surrounding voids, filament sheets, and so forth. Gravity will make that kind of structure for you, but it needs some help. And so that's another reason that we need dark matter. So what could it be? Let's see if we can prune back this tree a little bit. It's very easy to come up with ideas for what the stuff is, but can we rule any of them out? At this point, quite a bit is been tested because there is a Nobel Prize waiting for whoever discovers the dark matter. And so one of the first things you think is, well, maybe it's just very faint stars, brown dwarfs, planets, very small rocks, things that cannot easily be seen. And with very few exceptions, those have all been excluded at this point. If we look hard enough, we can figure out how to see something, even something very faint. And if you wanted to make it very small, like planet scale things, there really have to be a tremendous number of them to add up to the amount of dark matter that we think we need. So it's at this point very, very hard to sustain any kind of normal matter, even things like very small rocks. We ought to see if they are in just blocking. Even if they don't shine, they will block the light from background sources, and we'll be able to figure out that they're there. One particle that we know about that does not interact with photons, so it's dark by nature, is a neutrino. There are lots of neutrinos in the universe. They only interact through the weak force, so they're known that way. But ordinarily, they don't bother to interact with us. They just go right through us. And so that would make a good candidate dark matter. It's generally called hot dark matter because those things are moving at relativistic speeds, close to the speed of light. And it was a bit of a surprise, but it turns out these things do have mass, but it's also not enough. You know, when I first heard that, I thought, well, neutrinos aren't supposed to have mass, but if they do, that would surely be the dark matter. No, it's known that it is not enough. We have limits on how much that mass is, even though we don't yet know exactly what it is. We know it's not enough. And so that leaves us with cold dark matter, which we imagine to be some fundamentally new particle. One of the properties of which has to be that it does not, like neutrinos, interact with photons. So it's completely invisible. Usually these particles are assumed to be a WIMP, a so-called weakly interacting massive particle. So they interact through the weak nuclear force, the way neutrinos do, but not with light. So they're very dark. It doesn't have to be that, but that is the most common hypothesis. And this cold dark matter is motivated really by two very old now observations. One is that if you add up the gravitating mass that we can detect in the universe, it adds up to considerably more than what we think is allowed in the normal matter, the baryons, from Big Bang nucleosynthesis. And also, as I mentioned, the need to grow cosmic structure. There are other reasons, but those were the basic observations that got this whole ball game rolling. So one of the great successes of the past, really half century now, is that we understand, we think, how the light elements of the periodic table were made in the first few minutes of the universe, when the whole universe was one big nuclear furnace, and it converted some of the hydrogen into helium and a little bit of lithium. And one can calculate, there's a graph on the right, how much fuel there is, basically the baryon density. The more baryons you have, the abundances change. We can also attempt to measure these abundances directly, and they match up pretty well with what's predicted if and only if the baryon density is this small value of this density parameter. Note that we're nowhere near that magic value of 1. Normal baryonic matter does not get us there. But if we go out and measure the mass of the universe gravitationally by looking at how galaxies move out there, we get something more like this green band, fairly consistently between 0.2 and 0.4, somewhere in there. And you'll note that this is more than that. There's a lot of stuff gravitating out there that is not normal baryonic matter. So we need something else. Something outside the standard model of particle physics. And in the growth of structure, we go from this initial condition that we see in this temperature map of the cosmic microwave background. This is basically a snapshot of the universe when it was a few 100,000 years old. And you see all this structure now, but it took decades upon decades of hard, persistent work for us to measure these tiny temperature fluctuations that correspond to density fluctuations in the early universe, because really this is very smooth. And those little fluctuations that you can see are only 1 part in 100,000. Okay, so the early universe was extremely uniform. Of course, if you look at the universe now, 13, 14 billion years later, it's a picture of contrast. There are places of great structure like the Earth, the solar system, the Milky Way, and then huge voids of nothingness in between. It's nowhere near that uniform initial condition. Now, gravity will do that for you. It will take those little initial fluctuations that are a little more positive than others, and it will attract more to it, and the rich will get richer, and eventually you end up with this sort of structure you see on the right. But gravity is a weak force, relatively speaking, and the initial conditions are extremely smooth. So there's really not enough time to get here from there unless you do something to boost the process. And that's, again, what the dark matter does for us. Now, it took me a long time to wrap my head around this, but those statements that I've just made both assume that gravity is normal. Right? If Einstein taught us everything we need to know about gravity in the universe, then you absolutely have to have non-baryonic dark matter. And so that gives us this lambda-CDM cosmology. It's about 5% baryons. That green wedge is the normal matter. About a quarter is the cold dark matter. And the rest is the dark energy, which I'm not even going to try to get into here. But so mostly I'll talk about these things. And again, I want to note that we only really have direct knowledge of this 5%. That's the stuff we can see. So the WIMP hypothesis, these weakly interacting massive particles, have been the odds-on favorite for a long time for a number of reasons. One is that we've been able to rule out some of these other branches and prune them away. And so that leaves that. There are also some really theoretically appealing aspects of WIMPs, and the combination of those things led to them becoming the odds-on favorite that they are. So much so that for the past 30 years and more, we have been acting as if we knew for sure that this was the right answer. I remember, I think it was 1988, was the first time I heard a talk to this effect where some impressive speaker said that with great confidence that in 5 years we will know what the dark matter is. And 5 years later, I heard another impressive speaker say the exact same thing. In 5 years, we will know what the dark matter is. And every 5 years for more than 30 years, I've heard that statement repeated, but we still do not know what the dark matter is, except that in retrospect, it's abundantly clear to me that those speakers already knew what the dark matter was. They were sure it was these WIMPs. And I was guilty of that as well. It really was the obvious solution. So I want to mention this philosophical quip that has been attributed to many people. I think the correct attribution is Josh Billings. But what gets us into trouble is not what we don't know. Ignorance is okay as long as we admit it. It's what we know for sure that just ain't so. So that is to say that we get in trouble when we're absolutely convinced that something is true when it's not. There is a really obvious example of that going on in the politics of the United States right now. So the WIMP hypothesis is a good one. It makes predictions for how one can go about detecting these things in the laboratory. They should occasionally interact via the weak nuclear force, scatter off of target nuclei. And there have been many experiments at this point trying to do this, because as I say, there's a Nobel Prize waiting for whoever gets a detection here, and we're sure that's the answer. So it's just a matter of looking hard enough, right? Well, so this diagram shows the interaction probability, that is how likely a WIMP is to interact with a nucleus in a target detector. This is how much the particle weighs. 100 here, that would be about 100 times the mass of a proton. That's about what's expected for these things for really well-established theoretical reasons. And so this was sort of the early predictions up here. And by 2008, this region had been excluded. So this was reconsidered. It's been reconsidered many times, but it was 2008 when I first made this plot. And this prediction sort of factors in the fact that we already hadn't seen it there. And most of the predicted area was around here. There are good reasons for that. There's really very little chance that it lives down here. And yet, that is now completely excluded. So these WIMP particles, as good a hypothesis as they were, they've been excluded as originally conceived. Now we can reimagine them as having much lower interaction cross-section, but that's not really what we meant. So if you're interested in the history of this, I have a web page on that goes into this in more detail. Let's say it's just been a long-running disappointment that we have yet to see these things. Now, something that came up in my own work contradicts this story. And this came as a great surprise to me, and it's often dismissed by people who work on larger scale structure. And I stumbled across this quote from Tolkien's mythology, which I have paraphrased here. That a single galaxy might seem a little thing to those who consider only the immeasurable vastness of the universe, and not the minute precision to which all things therein are shaped. So yes, we need to explain the large-scale structure, as I alluded to, and dark matter does a good job of that. We also need to explain the precision with which individual galaxies work, and that dark matter does not do so well. So here we need to know a little more about galaxies. Here's a picture of that same galaxy in the optical part of the spectrum, something like what our eyes see. In the near infrared part of the spectrum, this is useful because it's a pretty faithful map of the distribution of stellar mass. Stars there, some in the spiral arms all around. And then there's also a gaseous interstellar medium, of which there's a map on the right. And these are all to the same scale. So the gas really does extend further out than the stars. Even though if you add it all up, there's more stars than the gas is more spread out. So one can measure the rotation curve for this galaxy. Again, this is a plot of how fast orbits are. Stars and gas are whizzing around. This is how fast they're going as a function of the distance from the center. And one can build what we call a mass model, that is, look at the distribution of stars in that central concentration we call a bulge, the stars in that spiral disk, the gas in the disk that's still on the screen here. And you can use the Poisson equation, which is basically Newtonian gravity's prediction. Or if you have that mass distribution, this is what the rotation curve should be. That black line is what you should get from the normal matter, the baryons. And you notice that falls well short of the flat velocity. Everything in between is the dark matter. So why is that? Well, it's not just that we have extra mass to make those rotation curves speed up. That was the initial hypothesis, but there's a lot more to it. Galaxies are very orderly systems, so they consistently have these flat rotation curves. But the amplitude at which they become flat depends on the mass. So these very massive galaxies rotate very quickly. Lower mass galaxies spin more slowly. And the correlation between those is very nearly perfect. It's a thing called the Tully-Fisher relation. So now each point in this diagram is one galaxy. This is the mass of the galaxy. This is how fast that flat rotation speed is. The big galaxies are always up here. The low mass galaxies are always down here. Of course, everything in between. And one thing to note here is that the mass here is the stars and the gas. It's what we can see. Nothing to do with dark matter. It's just how much mass we can see in stars and gas. Now I have to take a little diversion to define surface brightness better. Here are two galaxies on the sky survey plates in which they were discovered. Some galaxies are high surface brightness, so you can see that nice spiral galaxy just sitting there amongst the stars. All these little points are foreground stars in the Milky Way. That is an external spiral galaxy. This is high surface brightness. The stars are relatively concentrated. They're not packed in close to each other, but for the standards of space is giant, they're relatively close together. Other galaxies are low surface brightness, and you can barely see this slight smudge of a thing there. And that's entirely because these the stars in this galaxy are spread thin. They're very distant, relatively speaking, compared to that. So there's less light per unit area, and they're low surface brightness. And this is what I was interested in since my young days as a student. Here we zoom in on those images, and you still can't see much difference. But if you now take a much deeper image and turn up the contrast of this lower image so that you can see more details, then you can see they're actually fairly comparable spiral galaxies, about the same diameter. They're about the same distance away. And the real difference is just in the surface brightness, how tightly packed the stars are or are not. So I was trying to understand these low surface brightness galaxies, and I made a simple prediction for this Tully-Fisher relation, is that they should fall off of the Tully-Fisher relation that was then known for high surface brightness galaxies. And it's not just me, it's really just Newton. The velocity that we measure should depend on the mass of a system and its radius. And we don't know what the dark matter is doing, but you can see what the stars are doing. And by lowering the surface brightness of a galaxy, you're spreading it out. So for a given mass, you're making the radius larger. And that means that the velocity should go down, same mass, less radius. However, to my dismay, as I measured lower and lower and lower surface brightness galaxies, the data did not get the memo. So these lines are my prediction that just follows from that reasoning of Newton's, and yet the data all followed the same Tully-Fisher relation. They did not care about the fact that the radius was changing, and that seemed to me like a contradiction to Newton. Now, since that time, we've come up with lots of explanations for it, but there was only one theory that predicted that ahead of time. Now, the orderliness of galaxies does not stop there. The Tully-Fisher relation is just the total mass and sort of the amplitude of that flat velocity. Here are the rotation curves of a large sample of galaxies color-coded by surface brightness. So again, these are low surface brightness. These are high surface brightness. This plot was made by my former postdoc, Federico Lelli. And you see this beautiful rainbow structure from the lowest to the highest surface brightnesses. So it's not just the Tully-Fisher relation, but it's the entire shape of the rotation curve, which we think should be dominated by the dark matter. And yet that's completely predictable, or at least well correlated with the surface brightness of the stars. Nothing to do with the dark matter. So we tried to quantify this empirically as something we call the radial acceleration relation. As we noted, if you have all these different rotation curves, we now have 3 different galaxies, one with a big central bulge, one is sort of mostly a spiral disk, and one of these low surface brightness galaxies. And you can see the rotation curves look very different, right? The central bulge sort of explains the rotation of the inner few points, but then it flattens out and fails in the way we see over and over and over again. The same thing for the spiral galaxy, but as we get to a low surface brightness galaxy, you don't explain really any of that. Nevertheless, you can plot other things. This is the centripetal acceleration, just v squared over r. That's the force per unit mass that is required to keep a star in its orbit. And along here is what Newton predicts for that quantity, just based on the baryons that we see. And so if there were no dark matter or any funny business, all the data would follow that dashed line. Those 2 quantities should be equal. But you can see they bend away, but they bend away in a way that is the same for each galaxy. They just occupy different parts of this. So now we can pile up all the galaxies that we know about into this density diagram. There are now over 150 individual galaxies, and you cannot really distinguish the difference between them. So there are about 2,700 individual data points along the rotation curves of 153 galaxies here. And they all, within the errors, pile up on top of each other. So again, this is what Newton predicts for what we see on the x-axis, and on the y-axis is what we get. So if there were no funny business, this would be a straight line. But what we get is related to what we see. It's not the same, but it's related. And so you can predict this from that. And this bends at a critical acceleration scale of about 10 to the minus 10 meters per second per second. It's about 1 angstrom per second per second. Tiny, tiny, tiny acceleration, but that is what stars feel in their orbits in their galaxies. And we only really run into this dark matter problem near these very low acceleration scales. So this is sort of the amplitude of the discrepancy, i.e. how much dark matter we need relative to the normal matter as a function of acceleration over everything I could think of. So you are here. This is the sort of 9.8 meters per second that we live with on the surface of the Earth. Here are some very high acceleration systems. The last orbit of emerging pair of black holes, the first source detected by LIGO, the Gravitational Wave Observatory. What you expect for the surface of a neutron star that is itself on the brink of collapse into a black hole. Gravity works fine on all these scales, works fine in the solar system, and it's not until you get to these extremely low accelerations that you start to see a discrepancy. Now this behavior was predicted by a theory called MOND, for Modified Newtonian Dynamics, introduced by Monty Milgram. So let's chase up the other side of this tree, because it really is, a lot of the data are ambiguous. Some favor one branch or the other, but really all you know is that something is wrong. The gravity we know about applied to the stuff that we see doesn't explain the universe. So maybe it's not dark matter, maybe it's some modification of the equations. And so here is the idea is that, you know, our brains usually think, oh, well, galaxies are big. And so on some large size scale, the force law will change. And that's not how it works. Well, the scale that matters is not some giant length scale, but it's this tiny acceleration scale. So above this tiny acceleration scale, everything is normal. Newton and Einstein can do everything for you without dark matter. Below this scale is where we need dark matter, or this modification, which is just this craziest thing to look at. You just compute things as you would for Newton normally and multiply it in quadrature with this new constant of nature that just makes your head explode if you know any theory. Nonetheless, when it first became aware of it, and this was the mid-90s when I even first bothered to read the original papers that Milgram wrote back in 1983, and I really noticed this line. He said, disk galaxies with low surface brightness provide particularly strong tests. In 1983, most astronomers believed in something called Freeman's law, which asserted that all spiral galaxies had the same surface brightness. And much of my career to that point had been trying to convince them that, no, really, here's a low surface brightness galaxy. They exist. I can show you pictures of them. I can measure these things quantitatively. So it really caught my attention that Milgram was making predictions for this class of galaxies, which at the time were thought not to exist. So basically the data I'm going to show you didn't exist when he made these predictions. He came up with this theory is basically what can we do to change the force law to give a flat rotation curve. The rest of it is basically a genuine prediction, one of which is the Tully-Fisher relation. He had a particular slope that was predicted. Well, that is the right slope. With dark matter, it could have some other slope. It doesn't even have to exist as a relation. The normalization of this depends on the acceleration scale. Fundamentally, in this theory, there's no dark matter, so it's just a change of the force law. So it should be a relation between the stuff you can see, the mass of the stars and the gas, and flat rotation. Well, that's what it is. And the thing that really caught my attention is that it predicted this lack of dependence on surface brightness. This is something that I had predicted there should be a shift for, that I really could not understand the lack of a shift in conventional dark matter terms, and which I think the community still has not really wrapped its head around. But this just falls right out of Milgram's force law. So at this point, I was like, well, that's amazing. Still can't be true, right? So let's check these other things. One thing he predicted in 1983 was that if you computed the enclosed mass to light ratio, how much dark matter do you think you need as a function of radius and surface brightness, that lower surface brightness means lower surface density, which means lower acceleration, which means a greater amount of dark matter that you infer. Not that it's really there, you just infer that because you're in this lower acceleration regime where the effects of the modification to the force law are more pronounced. And sure enough, that's what happens. Same thing for the shapes of rotation curves. Remember, I showed you that beautiful plot with the rainbows from Federico. This is a much earlier version of that, but the same thing happens, that the shapes of rotation curves that Milgram explicitly predicted would behave in this fashion, that the low surface brightness galaxies would have gradually rising rotation curves that only slowly rolled over to be flat, whereas the high surface brightness galaxies would go up fast and maybe even fall a little before flattening. It's exactly what we see. And none of these low surface brightness galaxies were really known at the time. Now, in this theory, there's no dark matter, so a measure of the dynamical mass surface density had better correlate with the surface brightness of the stars you can see. And so that's an attempt to measure that, and that line is not a fit. That's just what has to happen. Again, that's not the reason that has to happen in any theory but MOND. So at its root, all MOND is a change to the formula that lets you map from what Newton predicts to what you get. All right, so it amplifies the Newtonian force by an amount that depends on the acceleration. So you go further out, the acceleration drops, the amplitude gets bigger, and this matches up. So when you do this, you can go and fit rotation curves. This was pioneered by my colleague Bob Sanders at the University of Groningen. And you can do this for lots and lots of galaxies. And the only freedom that you have in making these fits is the mass to light ratio of the stars. That is, we see the distribution of stellar light, but we need to know the distribution of stellar mass in order to do the calculation. So this is the one free parameter that is available in making the fits. And so you can do this over and over and over, and then you can go out and get a whole lot more data. And these are now fits made by my former grad student, Ping-Fei Li. And we can do this over and over and over. Mas, 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 mas. All right, we've done this for hundreds of cases now, literally. So here are the residuals of all those rotation curves fits. The color codes the quality of the data. The blue is the best data, green intermediate, gray the worst. The fits are good. There are the occasional goofy case. That's to be expected in astronomy. It would be weird if you didn't have those, but the vast majority of the data are well fit. So that's an important point because each and every galaxy has its own personalized mass distribution. So each and every galaxy is a unique test of this force law that Milgram hypothesized. And it works over and over and over again. So each and every galaxy is an independent test, and the theory captures details that are not explained otherwise. So here's NGC 6946 again. It has a strong concentration of light at the center that causes this little feature here. You can't do that with dark matter. It has to be the stars. Now, it could just be normal stars without dark matter here, but then there are a lot of galaxies like this one, much lower surface brightness, and here's this broad feature in the gas, and that is reflected in the rotation curve. That should not happen if the dark matter is what's doing most of that. The dark matter is completely dominant at this point, and it's arranged in some sphere made of stuff that's not baryonic normal matter at all. They just should not be talking to each other at this level. But you can basically predict, okay, I see this feature. I'm going to observe that feature. And you do over and over and over again. So I've done this exercise where I actually said, let's just close our eyes and try predicting these rotation curves, guessing at the mass to light ratio of the stars, not fitting them, just guessing at them. And so this is for the brightest galaxies, the first one I did. This is my best guess for what the stellar mass ought to be. You apply MOND, and this is the predicted rotation curve. And except for that little bit in the center, it's perfect. No hands. I'm not adjusting anything at all here. If I tried to do this with lambda CDM, well, then there are a lot more parameters I have to worry about, and there are about a dozen different ways you could do this. One I've used here is called abundance matching, which tells you, okay, the stellar mass of the galaxy is so much. That means the dark matter halo mass has to be so much more, and that fails horribly. Right? These are the data. This is the prediction. Now I could go through a menu and start picking some other choice for doing that, but there's no agreement as to how that should be done, and none of them work as well as this crazy theory of Milgram's does. So that's just one case. We can do it for all. Now I have 175 galaxies that I can do this for. And this is the residuals without any fitting whatsoever. These are the corresponding mass to light ratios where I've just assumed that they're all the same, except for some cases with big bulges. With the stars in the bulge should have slightly higher mass to light ratio. So it's basically just going from light to mass to prediction. So it's pretty well. And if you do the fitting, this is what I showed you before, then obviously that tightens up as you'd expect, because now you're adjusting the mass to light ratio a little to compensate. And here are the inferred mass to light ratios. And that's good, because if you know anything about stars, this makes your head explode. There has to be some scatter in this number because there are different kinds of stars in different galaxies. And so this scatter is what we expect, not that. And if you look in other band passes, so that was the Spitzer 3.6 band. If you look in the blue optical band or 2 micron band in the near infrared, you can ask, okay, well, here's the mass to light ratios of these MOND fits. What is the prediction for stellar populations? That is that line. That's what we expect for stars. That has nothing to do with the MOND fits. It's just using what we know about stars to do this. This particular model that I'm showing was made by Eric Bill, wasn't done by me. It just falls right in line. And on top of that, you expect more scatter in this bluer band and in the redder band. And so you can compute what that is. And again, that's what you see. So the fitted mass to light ratios in MOND cover the right normalization for the mass to light ratio, this dependence on color, and also the amount of scatter from bandpass to bandpass. Really could not be in better agreement with that. It really could not. So, you know, what am I supposed to say? That Milgram was wrong? Believe me, there's a huge temptation to say that, but really he's gotten many of these predictions right. So I keep trying to test this. An opportunity to do this came up in the early teens when the PANDAS survey was imaging. This is Andromeda, which is the nearest large spiral to us, which has many dwarf satellite galaxies, which are conveniently circled for you so you can see where they are. And they were discovering new ones. Some of them were already known, hence the red and the blue, but others they were discovering brand new. And with MOND, all I need is to see how bright that is, and I can predict the velocity dispersion. So let's do that. It's hard to show these data. This is the predicted velocity dispersion. That's the speeds of the stars within each one of these dwarfs. And this is for Andromeda 1, Andromeda 2. We're really good at naming things. Andromeda 3, Andromeda 4 turns out to be a background object, which MOND predicted it would be because it moved too fast. Andromeda 5, Andromeda 6, so on. So all these little dwarfs. And some of them, and people were doing the follow-up observation so fast that I couldn't really get the predictions out as fast as they were doing it. But in some cases I did. And so basically the predictions, you cannot distinguish from the observations where all those green circles are. For the yellow circles, and there's one case that's really problematic. So you could say, okay, MOND is falsified because it gets this one case wrong. But why does it get all these others right? Can I predict this with dark matter? No, I cannot. And it's not for want of trying. I mean, it's not just that I'm looking only at MOND. I'm trying to do this from every conceivable perspective. And a number of these got right in advance. All these little gold stars, those predictions were made before the observations were made. So that is the gold standard of a priori prediction in science. Now, one of the curious things about MOND, I don't have time to go into in great detail, is the so-called external field effect. This EFB is basically, MOND depends on this absolute acceleration scale. So mostly you have to worry about the gravity of the object you're looking at. But you also have to worry about the gravity of everything else in the universe. And for some objects, that can be stronger than the internal gravity. And that's true for some of these dwarfs. So you have to worry about whether something's all by its lonesome or whether it's feeling the effects of the gravity of a nearby giant host like Andromeda. There are enough of these satellites of Andromeda that you can pick out matched pairs, galaxies that on their own would have the same predicted velocity dispersion. But one is isolated, the other is affected by the external field of Andromeda. And that means it's not as low acceleration, so there's not as much of a boost from MOND, and so the predicted velocity dispersion is lower. And you can see that difference. It's most clear in this case, but you can see it over and over again. And that's important because this external field effect is unique to MOND. It has no corresponding thing in dark matter. It's just a unique prediction of MOND. MOND predicts this, it should be there, it apparently is there, and we have no good way of explaining that in dark matter. Very recently, my colleague Ki-Hoon Choi at Sejong University in Korea found a statistical detection, not just for the little dwarfs nearby to us, but for giant galaxies at much greater distances. And the takeaway here is that the best fit for the value of the external field effect is non-zero, and it's significantly non-zero. Now, obviously, the errors are still big. We even occasionally get something negative, which is unphysical, but that's just because this is really hard and the uncertainties are big, and so things are smeared out. What really impresses me is that the peak of this is significantly non-zero. That I did not think we would be able to detect, but he worked really hard on it and achieved it. All right, so I should try to wind up a little bit. Let's go back to what Newton said, because I get complaints all the time from my colleagues. Oh, you're abandoning Newton. I would say no. What Newton said was that everything happens as if the force between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. His famous inverse square law of gravity. And that's what this equation is. The acceleration, that is the force per unit mass, depends on the mass and the inverse square of the distance. Okay. Now, at the time, this was seen by his colleagues as a kind of magical thinking. How does one object affect another object far away? They have to be in contact in order for a force to be exerted. This is totally insane. And what are you talking about? And that's why Newton was careful to say everything happens as if. He's saying, okay, I'm not saying this is really how the world works, but it sure looks that way. And so I would make the same statement now, regardless of what's going on at a fundamental theoretical level. MOND is the effective force law in galaxies. Everything in galaxies happens as if this modification of that Milgram suggested is what's working. Now this leaves us in a terrible bind because Newton led us to Einstein, who leads us to this lambda CDM cosmology that's full of dark matter. Now Milgram wrote a theory that contains Newtons, just as Einstein did, and that explains galaxies. But these things do not go together. There is no theory that does all three. And that's what we really want. Some grander theory that encapsulates all these things, and we just don't have such a thing. And such a thing is not easy to get, right? One does not simply write down new equations of gravity. And so this is not a problem that's going to be solved overnight or really anytime soon. There has been some progress. Bekenstein made some progress, some important work recently by Skordas and Zlotnik. Others have worked on this. We're not there yet. That's good. There is still fundamental science to be done. If somebody says, oh, we've discovered everything there is to discover, that's wrong. There are fundamental problems that are still open. The bad thing, we're still sort of currently floundering around in the dark. And we argue about this a lot without a lot of noise. So I'm going to end by playing a video of my daughter and the daughter of colleague Tom Schutt, who is somebody who works on these dark matter detection experiments. And of course, we would claim not to bring our work home. But one time I did, we were at a conference in 2008, where I showed the limits from. And it happened to be my daughter's birthday. And so when I got home, having just talked to Tom and seen everything shut, my daughter's best friend, Maddie, Tom's daughter, was there with a bunch of other kids. And I walked in and said, oh, Maddie, hi, I was just working with your dad. And she looks at me and said, I thought you worked against each other. And so there ensued this argument between the girls, which Tom obsessed about reproducing. And it went something like this.
So have you finally given into the idea that dark matter doesn't exist?
Dark matter does too exist. If dark matter didn't exist, then the eighth dimension would not fit into the quantum theory. No. We have tested it. No. The eighth dimension does not be divided by 4. The quantum theory of 8.
And that's where we're at. Thank you for your time.
Bravo. Thank you so much, Stacy. This is a wonderful end.
Well, I hope it was good. It's always strange just talking to your screen. So.
Yes, we're all here. So there are a lot of questions in the Q&A.
I have many questions. So.
And I'm sure the panelists have also many questions. So let's start with Cole.
Wonderful talk, Stacy, and I appreciated all the Python references. And you mentioned at the end, of course, there have been attempts, not yet successful, to have a fundamental theory which can produce the phenomenology of MOND. But if we adopt the hypothesis that there is no dark matter at all, is the behavior of clusters something that can give hints to what such a theory must predict in that slightly different environment than focusing on the galaxies?
Yes. Next question. No, let me say more on that. So what is Cole alluding to is if earlier in my talk I did have clusters, and I realized I would not have time to talk about them in detail, which I didn't have as much time as I did to talk about what I said, so I didn't. But what you see in clusters of galaxies, as opposed to individual galaxies, is that MOND as a theory does not go far enough. That is, it wants still more dark matter than it can explain by itself. So what some of the suggested, and Cole has alluded to, is that perhaps when we get some more general theory, that it will have some extra piece to it that makes up that difference in clusters of galaxies. I hope so. People have tried that as well. The thing that comes to mind is a theory called E-MOND by Hongxun Zhao and Benoit Famei. And so in the Lagrangian for that theory, there's a term for the depth of the potential as well as for the acceleration. So that at least goes in the right direction. I don't find it very satisfactory. I'm also mindful of the history of the mass discrepancy in clusters because when Zwicky first found that in the 30s, of course, the mass to light ratio of clusters were in the hundreds. And, you know, okay, so it's all dark matter, right? Well, of course, that turns out not to be true. At that time, we did not know about the X-ray gas, which turns out to outweigh the stars and the galaxies in clusters by a large factor. So really, there were two missing mass problems in clusters. One was that we just hadn't accounted for all the baryons. So I'm still a little worried that that might still be true, right? We need a lot. It's like a factor of 2. And that's not something I can suggest a sensible model for. But I'm also not, you know, mindful of that history. I'm a little leery of just saying, oh, well, it can't happen.
Thank you.
Okay, before we move on, I forgot to put the 1.5 minute break for everyone to calm down and read the Q&A and vote up questions that you like. So let's take the little break now, so our interpreter can have also a little rest. And in meantime, I want to say happy birthday, Stacy.
Thank you.
It's just 4 days.
It's recent. Another tick around the calendar. I've been doing this stuff for almost half my life now, so that's kind of scary.
Yes, another round. Yes, so happy birthday. So I encourage you to please look at the Q&A. There are many very good questions, so please vote them up. So we're going to take a very short break. Okay, so let's start refreshed with the question from Emanuela. Emanuela?
Sorry, I had the microphone on mute. Okay, my own question is more a curiosity because I know that MOND is a phenomenological explanation, but do you know if there is some theory that is looking at the particle counterpart of gravitational wave?
So something like the graviton.
Yeah.
Yeah, so I don't know that myself. I do know that since, as you say, that gravitational waves have been detected, then you have to satisfy that as a requirement on any theory. So there were some ideas like Bekenstein's Tevis, which could have a difference in the speed of propagation between gravitational waves and the speed of light. And that's excluded now. So whatever, you know, as a powerful constraint on theories, it has to do just that. But I don't know what the what the particle physics implication of that is.
Then we have a very nice question from one of the listener that says, basically, what do we need to know about dark matter to say that we know about it?
Well, we need to detect it. That would be the best thing. So, I mean, there are lots and lots of laboratory experiments looking for it. But in order to construct such an experiment, you need a good hypothesis that makes a prediction for what to look for. And so WIMPs are one idea. Another I didn't talk about is axions. This is a very different kind of particle, but still you can work out what the particle ought to be and figure out a way to detect it in the laboratory. And that's great. And so if you detect it, then that's the thing. The downside is that if you don't detect it, you don't know when to stop looking, right? How hard do you have to look before you move along to the next particle? And then you can always move along to the next particle, to the next particle, to the next particle. There's now dozens and dozens of serious ideas out there. And how do we get out of this if that's not the right way to go?
Okay, let's go to the next question by Rohan.
Hello, that was a very good talk. I have a question which is similar to one of the questions from Q&A from Carlos Rodriguez. You highlighted a bit of it on external fields. So he talks about the findings of two galaxies, I think it was DF2s and DF4s, which were said to be missing dark matter, and how I had read in the paper you showed that it was due to the external field. So if you could highlight more about how absence of dark matter can have implications on the MOND theory.
Right. So MOND, being a modified force law, it has rules that you write down in those equations, and once you write them down, you're stuck with it. The funny thing, as we're talking about, is this external field effect. So basically, the amount of dark matter that you need depends on the total acceleration. And it doesn't matter whether that acceleration is provided by the internal gravity of the object or some external source. So in the case of a galaxy like NGC 1052 DF2 or DF4, they are satellites of the giant galaxy NGC 1052, so you have to take its gravity into account, just as I discussed for Andromeda and its satellites. So when there is an external source of gravity like that, then the total acceleration is higher, still very low, but higher and closer to that magic number of Milgrams, this A0. And if you get over that scale, then there's no dark matter, or at least you wouldn't infer it. And so how much depends on how low it is. Now, in that specific case, it's important to note that it's still a little below this limit. So there should be some effect. It's just at present too small to detect. So when you say, okay, is this galaxy consistent with no dark matter? With the nears, that's correct. Is this consistent with MOND? That is also correct, but they are slightly different. And so hopefully we can measure that better in future.
Thank you.
Okay, so let's go to the Q&A, and one of the top questions, or the two actually top questions, come from Gaspar Galas. He says hi.
Hi, Gaspar.
And he's wondering why black holes have been discarded so quickly as an option for baryonic dark matter, and is it so evident to discard them right now? Surprises from LIGO, right? We have evidence for intermediate mass black holes. There is now this swarm of stellar mass black holes around the Milky Way core, right? You have maybe primordial black holes. So can you talk a little bit about that?
Sure, though Cole may be the better person to do that. So, this is an old idea that maybe the dark matter is primordial black holes. If that's true, you have to make them extremely early in the universe before the era of Big Bang nucleosynthesis, which is, ends at 5 minutes, right? So you have to take a very smooth initial universe and convert a lot of it into these, densest possible things in no time at all. So that just seems implausible. Now, we do know black holes exist. It's a matter of whether there can be enough of them to do what we need them to do. And so people have done these microlensing experiments where they watch for the magnification of the light of a background star as some dark object like a black hole passes in front of it. And that's been detected, and that puts limits on how much of that stuff is there over some mass range. And so as long as, I think that goes from basically a Pluto mass up to maybe 10 solar masses. So you could imagine getting away with something like a 30 solar mass black hole, which is, you know, kind of typical of what we're seeing from LIGO. So that is certainly a possibility in that regard. I think it's still hard to make them. I think it's hard to have them enough of, but it's a possibility. What bugs me is I don't see any way of using that to explain the phenomenology I was just talking about.
So another related question also from Gaspar. Does MOND predict any angular momentum, let's say scaling relations, that is sort of a diagnostic in galaxies with contrast to standard dark matter?
Well, so certainly they're related, but they sort of collapse in MOND. That is, in conventional terms, you have something like Tully-Fisher, relation between mass and velocity, but then angular momentum also includes the size of the galaxy. And that just gets collapsed out in MOND. So you can write down the angular momentum just as you can write down Tully-Fisher, and it's just a function of the mass, not both, once you get into the MOND regime. And that's the thing that actually attracted my attention, was that, you know, the argument I made about Tully-Fisher and that there should be some shift, that is essentially an angular momentum argument. And you're not seeing that, at least not conventionally. You're seeing what MOND predicts.
All right, let's go to Matt.
Yeah, hi. Thanks so much, Stacy, for that really great overview. The question I was going to ask was actually just asked. That was Gaspar's question. Hi, Gaspar. But there is another related question in the Q&A that I thought I'd tack on, which is, you know, there's a lot of news. So this is from Tim Bray. There's a lot of news about these quasars that are being discovered at higher and higher and higher redshift, meaning that these supermassive black holes are really having to form at increasingly earlier and rapid rates. Does that add any additional constraints to either MOND or Lambda CDM? Feel free to reference your just recent answer if that makes it easier.
Well, no, that's a really good question, which I will generalize on a bit. But first, just for specifically black holes, again, Cole here is an expert on exactly this, and it is. At least it has been, maybe it's been fixed, but it's a lot of mass to put into a point in the very early universe, right? So you have to get rid of the angular momentum in the gas to pack that down. Now, once you start doing it, it proceeds pretty quickly. So the trick is, I think, getting those seeds in place. But more generally, and this is where I'm going to generalize on this, is that we do want to understand the formation of the structure in the early universe, not just black holes and quasars, but galaxies in general, and the whole wide web of structure that they eventually turn into. This is something that's extremely well simulated in Lambda CDM. We understand how this is supposed to progress. Bob Sanders and I both independently tried to do this with MOND about 20 years ago, and what we found was that you know, well, galaxies are easy in MOND, they're hard in Lambda CDM, and vice versa. Structure of formation is straightforward in Lambda CDM, and it's hard in MOND. But the important takeaway that we did find from that is that structure will form fast in MOND, faster than in Lambda CDM. So you expect big things in place at higher redshift than you do conventionally. And so that's a test that you know, eventually we should be able to do. Maybe we're already doing with these very early quasars. So just to give another example is the so-called edges detection, the 21 centimeter absorption at redshift 17. That just should not happen in Lambda CDM. So most of us are just holding our breath that, no, that's wrong, it's going to go away. it's an early detection. Maybe that is what will happen to it. But it actually, I had to go back and read my own papers from 20 plus years ago. It's exactly the sort of thing that we predicted would happen. So.
Great, thank you.
Let's go to Davor.
Yes, hi. Thank you very much for this beautiful talk. I would like to ask you another question. It is related to the fact that all the data that you showed were from nearby galaxies. What about more distant universe? Is it a problem that the data that we get from redshift of 1, let's say, like rotation curves that people are observing, are just not going far enough? Or because there are many studies coming out with Tully-Fisher relation at redshift of you name it. Can we use those data to test whether MOND really works or doesn't?
Sure, that's a great question. So first of all, I would say yes, we're using local galaxies, relatively speaking, for which we can get really good data, and that is key. You can expand that sample by lowering the quality threshold, and then a lot of the things that I've talked about are less clear. As near as I can tell, that's entirely a consequence of lowering the quality threshold. You throw mud at the wall and there's mud all over the wall, right? So that problem becomes more severe at high redshift, where it's just naturally harder to get good data. And I don't want to try too much to pick and choose who to believe and not. The nominal expectation I would have for MOND with a fixed acceleration constant, presuming that does not evolve in time, and then Tully-Fisher should not evolve in time, and that would be the baryonic Tully-Fisher, so you do have to do all the stellar evolution right to get the mass to light ratios right. And the last I checked, Sarah Miller had done a really excellent job with that and found no sign of evolution out to redshift 1.5. But other people find other things, so you do end up having to pick and choose who to believe. So hopefully those data will continue to improve. I know of, so Federico Lelli, who I mentioned earlier, has done some really impressive observations with ALMA at very high redshift galaxies, and they seem to behave more or less as we'd expect. Problem when you get there is the stellar mass gets really hard to constrain. But I think the picture at high redshift is still developing, and so I don't see anything in the data that I believe so far that makes me believe that there's any problem for MOND, or even that there's any evolution in the acceleration scale, which in principle might happen.
What about, so related to that, what about the Lyman alpha absorber densities and sizes? Like that is like the classical thing that people always throw up, right? Because it's in this low acceleration regime, and it's all over. So you can look at, I don't know, quasar sightlines and then look about the compactness of these systems. Isn't that a very good diagnostic?
So this was first done by Aguirre and his collaborators, to my knowledge, actually applying MOND there. And if you go and do that and assume they're all in the deep MOND regime, which that they're isolated, the first thing, then it's a terrible problem for MOND. And so I asked him, well, there is this external field effect. What does that do? And then that changed the answer by several orders of magnitude. So it went from being, a factor of 500 off to being a factor of 2 off. And then I'm like, well, what are you using for the external field? And I had my own estimates of what that number ought to be, and it evolves differently. He was using a lambda CDM number, and so it was a lower number at the redshifts than I would have guessed for MOND. So I don't know if it's right, but it's much closer in the ballpark than you naively would get if you just do the back of the envelope thing without really thinking it through. And I have seen that over and over and over again, that, I will see things, aha, I've discovered something, this will disprove MOND, and then I go through it and it's like, oh yeah, actually that's about right. It's really frustrating, actually.
Yes. Okay, I have another question, but let's go to Ellie next.
Yes, so one of the most voted questions here in the Q&A is from Felipe Orellana Soto, and he's asking, have someone ever wondered why haven't we seen matter orbiting dark matter?
Ooh, I can see why that's upvoted. That's cool. I don't think anybody's looked at it quite in that phrasing. People have looked for evidence for invisible galaxies. That is, objects that you just can't see but have gravitational effects. And there are some claimed detections to that effect, gravitational lensing by what are inferred to be subhalos within the halos of a dominant galaxy. So, you know, if the standard lambda CDM picture is right, not only do galaxies reside in a dark matter halo, but they have a lot of subhalos that should hold these dwarf galaxies. And some of those should be completely dark. So you might, in effect, expect to see something orbiting around that dark object, or like I say, the gravitational lensing effect is one way that's been looked for. Like I say, there are some claims to that effect. I don't want to dismiss them. I've spent a lot of my career working on low surface brightness galaxies looking for things that were nearly invisible. And when you look hard enough, there's usually something there. So I don't know is the answer if somebody's found that, but people are certainly thinking along those lines.
All right, let's go to Indranil.
Yeah, so I thought I'd answer some of the questions that have been raised. So first of all, regarding the gravitational waves, there was the paper by Scottis and Zlosnik from last year in which it's possible to create a relativistic MOND theory in which these gravitational waves travel at the speed of light. That includes the perturbations, so the Shapiro delay issue. It's addressed in the paper. So that's one thing. The other thing regarding evidence for or against MOND from sort of higher redshifts, so looking beyond the local universe. So yes, it may be difficult to do like rotation curve work at redshift 1, but regarding the issue of structure formation, especially things like quasars, we recently did a study in which we showed that the properties of the El Gordo galaxy cluster rule out the lambda CDM cosmology at more than 6 sigma significance. And this was generically what you expect in MOND, that structure should form more rapidly at high redshift. And in fact, there was a particular MOND cosmological simulation, which has been set up in a particularly realistic way, like a cosmological simulation, which actually gives you just the right number of El Gordo analogs in the surveyed region. So that's one thing. But to move this field forward, so there's one question on what might be sort of the single most useful piece of evidence to kind of settle this issue of whether you have MOND gravity at low accelerations or the Newtonian gravity continues to work. So different people might give different answers. My personal opinion, based on what we know now and the currently available technology, is that the most promising near-term test would involve using wide binary stars in the solar neighborhood. So stars with a separation of approximately 10,000 astronomical units, which should orbit each other about 20% faster if MOND gravity is correct, rather than the Newtonian gravity. So this is very promising because there shouldn't be any dark matter on this scale. It will be dynamically relevant. So yeah, that's what I wanted to say.
Interesting. Thank you. Very interesting. So I have here another question from the Q&A from Hans Zinnecker. And he's asking, what about the covariant scale invariant theory of gravity developed by Andromeda and Geneva? It seems to explain a lot of rotation curve data of this.
Right. So there are lots of people working towards this in different ways. I think there's some interesting things there. It's not exactly reproducing all the phenomenology that I see, but it's hard to keep track, and it's certainly a good idea. I think more generally, I should note that, I've phrased this as a modification of gravity, but really it's a modification of dynamics, and it might not be the gravity side, but the inertial mass side of things that for some reason, in some Machian sense, perhaps, that galaxies might, or objects in a low acceleration regime may be closer to some universal frame, and so they get easier to push around because their inertial mass is less. So it's not necessarily that you need to make gravity stronger, but that you could also break the equivalence between inertial mass and gravitational charge. That's even more radical, and I have even less idea how you do that, but it is a logical possibility that we should bear in mind.
Yeah, I mean, the breaking of the strong equivalence principle will, I think, percolate into quantum mechanics, right? Like,
well, indeed, we have no agreed quantum theory of gravity, do we?
That's correct.
So, I mean, I guess I say that because, there are very different communities of scientists who work on these things. And if I talk to cosmologists, they're like, well, you cannot abandon general relativity and talk about this. It's a non-starter. I understand where they're coming from. But if you go to quantum gravity theorists, of course, their starting point is that general relativity is incomplete, right? And so it may be that this phenomenology is some kind of hint that there is something more to do it. If we're playing solitaire with an incomplete deck of cards, we can never win. And we're never going to get a quantum gravity theory if we don't incorporate something that we should be incorporating.
All right, so we need to slowly wrap up. So let's go to Paul Heunigen next.
Yes, can you hear me?
Yes.
Yes, thanks a lot for the wonderful talk. I want to put the problem we are in today with dark matter versus MOND in a larger historical perspective, because I think the situation is very analog and analogous to the situation 150 years ago. So I describe our situation now. Mainly, we have some motions of celestial bodies. We have a set of equations which are wonderful, well confirmed. We try to apply these equations to these motions and find, well, we don't get everything. We get a lot, but there's a discrepancy in the end. Now go back 150 years in the 1860s. There was this famous French astronomer and mathematician, Le Verrin. And he, for the first time, really measured very carefully the motion of Mercury, right? And the motion of Mercury was then tried to be explained by Newtonian dynamics. And the story is this, that up to 0.7%, you could wonderfully calculate that. Very complicated calculations. It's a 200-page book because you have essentially a 8-body problem, right? And you had to solve it without a computer, but really making approximations is very hard, but it was extremely successful, up to 0.7%. So you had to add, all the influences of the planets and blah, 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 geometrical effects. So people were somehow happy, but they want to get rid of these 0.7%. And then the first idea was in such a situation, in the same way we are today, you either change your fundamental equations or you change some of the parameters, initial conditions, boundary conditions. Meaning, for today's situation, we leave general relativity in place and say, oh, there's additional matter, and then we get a different effect on other bodies. And in the same situation, or we say, okay, we change the equations and do MOND and stuff like that. The same was the situation in the 1860s. So most people then tried to stay conservative. They didn't doubt Newton. That was successful for 170 years or something. And then they said, okay, we've got to invent something else, namely more matter. And that was Vulcan, a little planet inside of Mercury. And they tried to find out whether that would make the changes in Mercury's orbit. It did, but it wasn't visible. It wasn't observable. Then people said, yeah, it could be planetoids, and it could be this and that, and it could be a quadrupole moment of the sun, and so on and so forth. So people stayed there on the conservative side, did not really consider deep alternatives. That only happened after Einstein started his business, which was 45 years after the discovery of the anomaly. And most people said, yes, it's a nuisance, but basically we got 99.3% of the effect. It can't be something fundamentally different. And nobody believed that until Einstein came up, and these remaining 43 arc seconds, that was the fundamental thing, that the prediction was so precise. And then everybody said, oh, that can't be an accident. So the point is what we learned from here, and I was very happy that you were so critical about those people who are too sure about, dark matter existing or whatnot. It's completely open what is going to happen. So nobody believed that 45 years until Einstein came, and this just then fell out, the precession of the perihelion of Mercury. It was a very small effect, but look, the step from Newtonian mechanics to Einstein was gigantic if you look at the difference between these two theories. So what we may expect, if we are now in a situation similar to that one, which is not sure at all, it's completely open, it may be that the step away from general relativity to something new is even much deeper than this modification that MOND introduces, and then you can play around with it. So we should be very, we should have much humility, concerning that situation. It may be many surprises around the corner, and nobody knows where we have to go. So your talk was so wonderful because I'd never seen this strong parallel with this Newton case, but I think it's very good to make us intellectually very modest. And I love that very much, your attitude in that respect in your talk.
Well, I came by it the hard way because I was one of those people who was absolutely convinced it had to be WIMPs. And I was deeply shocked when it was not my predictions or any of my immediate colleagues' predictions that came true in my data, but Milgram's. This was completely outside of my conceptual framework.
Yeah.
And I struggled hard with that for a long time. And it did require me to wrap my head around, well, geez, maybe I have been wrong at this very deep level in assuming that. And I think that's where we still are. I would say it's very hard to progress as a community until everybody has that experience, right? I've tried to make predictions for MOND in the hopes that, okay, well, it happened in my particular thing about low surface brightness galaxies. How about, you don't care about that, you care about the cosmic microwave background. Okay, well, here's what the first to second peak ratio should be. And that came true. And some people paid attention to that. But on the whole, I've noticed that community has made up an entire false narrative as to how I didn't really make that prediction. It's really, it's very hard to wrap one's head around.
Yes. Yeah.
Well, on that note, thank you so much to everyone. Thank you, Stacy, for this wonderful talk.
My pleasure.
For taking the time to talk to us. And thank you to the panelists for being around and asking great questions. Thanks to the audience for joining us. Please be so kind and fill out the survey at the end of this Zoom webinar, so it will show up as a web page after you log off. Thank you all again, and I hope we will see you on the next Golden Webinar in Astrophysics, which is scheduled on January 22nd, which will be given by Daniela Calzetti. She will be talking about understanding of the evolution of galaxies, how to tease star formation out of dust. So that's very interesting. So let's hope we see everyone again. Until then, please stay safe, stay civil, stay healthy, and until the next Golden Webinar in Astrophysics. Bye, everyone.